I'll mute myself, and yeah, good luck, Anna.
Thank you.
Thank you. Thank you for the talk. See you later.
Well, wait until you see it. Don't thank me yet.
Okay. I'll take the advice.
I've planned for like 45, 50 minutes to leave time for questions. That's the right thing to do, right?
That sounds good to me. Yeah. I think that should be good.
Mm-hmm.
Let's see how many questions we get. As I told you, it's like weekend afterwards, so I don't know how keen will people be.
Yeah, I mean,
questions.
If there's no questions, then you can start your weekend earlier. No one has ever been mad at that. So. Yeah, I always think in case of doubt, end sooner rather than later.
Absolutely.
Yeah.
So people should start joining.
Yeah, for sure.
I double checked on Costache, by the way.
Ah, thank you. I gave an invited talk at the joint maths meeting a while ago, and they also checked. They asked me how it was pronounced before, which I thought was really nice because people don't normally. Yeah, but I appreciate it.
I mean, I think it's like normal. I don't know. I have heard all sorts of weird pronunciations of my name. So it's like, yeah.
Yeah, I've seen people even drop parts of your name, I think. Or I think you told me this.
Yeah, a lot of people, so that's the thing, middle name, sorry, but still like some people go like, oh yeah, Eduardo Vázquez, like, what else do I have to do? I have already motivated my surnames to like, yeah. It's kind of fun, like all the different, like Soraya or pronunciations like that.
That's like a whole different name.
Yeah. Yeah, it's basically like I'm called like Soraya, like as a girl name, right? Like,
Yeah, there's a. Well, for me, I find for a name that's so many people are called a version of Anna or Maria, and for how easy it is and how common it is, I get so many misspellings, and I get E's thrown in theirs or double N's or, even gets put into two words. And because I guess maybe because I ask people to call me Anna, they kind of end up thinking that it's two names.
Yeah.
Anamaria, but yeah.
Yeah, I can see many Spanish people that would be doing that, like two names. And, yeah.
Actually, even in Romania, it's more common for it to be two names. It's not, I'm not like the only one in the country where it's one name, but it's far more common to be two names.
People are very slow.
Yeah, people are starting to join now. Maybe we can wait a couple of more minutes, Edu,
We can
give them some time.
Or something.
Okay, sounds good.
How many people do you think would be like quorum for participants?
So far we have 15 attendees.
Andrew told me there are 54.
54 registered.
Yeah.
Okay. Sounds good.
So let's wait maybe like 2
2
minutes or something.
Yeah, we can wait until 5 past. Yeah, I like treating virtual meetings like real life meetings. You need You need 5 or 10 minutes to go from one meeting to the next.
Yeah. Yeah, and to talk about the weather and these sort of things.
Yeah, I've noticed, especially when it started, but still now, you know, when all the meetings all of a sudden started being online, you'd get 5 meetings back to back with no, you know, not even a 5-minute break. And it's like, okay, it's you need 5 minutes every now and then.
Yeah, I can't agree more.
So the number seems a bit more stable in 35 participants. Maybe we can start.
Sure.
Okay. So hi everyone, and welcome to this talk at the CRC seminar series. Today I'm particularly happy to introduce to you Anamaria Costache, who is an associate professor at NTNU, which is the Norwegian University of Science and Technology. She's also a part-time employee at Intel. So prior to joining NTNU, Anna was a postdoc at the Information Security Group at Royal Holloway. And before that, she also worked as a research scientist at Intel AI Research in San Diego. She completed her PhD at Bristol University under the supervision of Professor Nigel Smart. So we are like research siblings if you check the Math Genealogy project. And yeah, so she's interested in privacy preserving machine learning, fully homomorphic encryption, and more broadly computing on encrypted data, lattice-based cryptography, and post-quantum cryptography. Today she will be talking to us about advances and challenges in fully homomorphic encryption, which is a particular area of expertise for her. So I hope you all enjoyed the talk, and yeah, the floor is yours, Anna.
Thank you. Okay, so hi everyone. Thank you for the invitation, first of all, and second of all, hopefully the next time around it will be in person. So as Eduardo said, I'll be talking about fully homomorphic encryption, advances and challenges, and so I'll start by sort of introducing FHE, talking a little bit about the history and some applications to motivate it. I will then talk about what, to my mind, is one of the biggest challenges in FHE, which is namely noise, but I will define this and talk about it in detail at that point. I'll also, if we have time, I'll also give you a flavor of the mathematics of FHE. So kind of by training, I'm more of a mathematician than a computer scientist, but don't worry, I won't be talking any sort of very involved or very technical maths, but I just want to show you or give you some idea of the kind of maths that's involved in building FHE and just sort of how cool that is. And then I'll conclude, and I'll talk a little bit about some open problems and some interesting research directions. So I've planned for about 45 minutes, just to leave some time for questions. But if you have questions as the talk goes, just feel free to interrupt me. But just know that I can't really see the chat. So either Eduardo or someone else is going to have to interrupt me, or you can also just unmute yourself and ask questions. Okay, so I'm sure a lot of you, if not most of you, if not all of you, have heard about FHE, but let me just still define it. So fully homomorphic encryption, or maybe more generally homomorphic encryption, is a type of encryption that allows you to compute unencrypted data. So you can have a scenario where you're the purple person on the left and you have some data that you want to perform a computation that I denoted by F. And I say I denoted, this is actually Rachel Player's image. So I do thank her for this. So you, again, you're the person on the left, you have some data, private data X, and you want to perform some computation F on it. But for whatever reason, you can't do it yourself. So, you know, kind of some very popular applications are you don't have the computing power. Maybe it's a very, you know, maybe your X is actually a large database and you just don't have the computing power to run your computation on it. Or it could be something like X is your medical data, your private medical data, and then some hospital or maybe some startup or something like this has a proprietary algorithm that they can run on your medical data and give you, you know, insights about your health. So think personalized health. And their algorithm is proprietary. Your data, you know, you wish to keep it to yourself. And so what you're going to do is that you're going to encrypt it with homomorphic encryption, send that along, you know, to the cloud or the entity that is going to perform this computation. They will then just simply apply this computation F to your encrypted data X. So the yellow square here represents something that's an encrypted form. And because of the way homomorphic encryption works, applying this computation to a ciphertext directly corresponds to or will directly output an encrypted form of f of x. And so then they send you back and then you can decrypt it. So, you know, you've performed the computation on your data and you've also kept it safe at all times because it's never been outside of, you know, your computer or your database in unencrypted form. So the cloud has never at any point had access to your data in plain text form. So that's roughly what it is. If we get a little bit more specific, in homomorphic encryption, the encryption function is what I call an approximate morphism. And by approximate, I will go into more details, but what I mean is that you can't just do operations forever. You have to do these so-called noise management operations. But if you forget about the approximation, what I mean is that whether you encrypt A plus B, or if you first encrypt A and then encrypt B and then encrypt the encryption of A and the encryption of B, you get the same thing. And so, you know, it's a group morphism if you can do either addition or multiplication, and then it's a ring morphism if you can do both. And so kind of homomorphic encryption refers to, you know, to the group morphism setting where you can do one homomorphic operation. And then what we're really interested in is the setting where you can do both, because that's what's the most interesting. And so a little bit of terminology, you know, if you've read a little bit about FHE, you'll see that there's what we call fully homomorphic and then somewhat homomorphic. And so what this corresponds to is fully homomorphic is the situation where you can do an arbitrary number of computations. So you're not limited by the number of additions or multiplications that you can do. And somewhat homomorphic scheme is where you can do additions and multiplications, but only a predetermined number of typically multiplications, because multiplications are more expensive. And so this is kind of equivalent to saying that you can homomorphically evaluate circuits of at most a maximal depth, or, you know, circuit or polynomials, or of at most a fixed maximal degree. So this is just really imposing a condition on your computation F here. And most of the schemes that we're interested in are based on the ring learning with errors problem, which if we have time, I will discuss a little bit later in the talk. And I will focus exclusively on the so-called second generation ring LW schemes. And I will remind you of this because I will say certain things that don't quite apply to all the schemes. But let me just tell you quickly about the generations, because again, if you know a little bit, but not too much about FHE, you might have heard of the different generations, you might have heard of different schemes and not, not know too much about, what these generations represent and what the differences are. So the first generation is more or less in the Gentry's original scheme, which was in 2009. And by the way, this is a non-exhaustive list. Of course, there were, it's not just Gentry's original scheme, there were some variants, but this is what is meant by the first generation. The second generation is schemes such as Bgv and BFV, which I'm sure some of you will be familiar with. I've put NTNU in brackets, and there's also Yashi. And the reason why it's in brackets is that it's technically in the second generation, but we know now that NTNU and Yashi are insecure in the parameter sets that is required for FHE applications. So the NTNU problems can still be used for some things, but not for FHE, unfortunately. So it's more of a historical mention. And then we have the third generation, which is comprised of schemes such as GSW, Phe, and TFHE, which again, TFHE is fairly popular, so I'm sure you might have heard of it. And then we have the fourth generation, which is much newer. And this is comprised of the scheme CKKS and its variants, again, non-exhaustive list. And this is, so the CKKS scheme is really very similar to the second generation schemes, but the main difference is that CKKS has this approximate computation. So in terms of, if you look at a CKKS ciphertext, it looks very, very much like a Bgv ciphertext. And, so does the algebraic setup and so on. But the main generation is that CKKS, the main difference, is that CKKS is an approximate scheme. And it can also handle certain floating point arithmetic much better than schemes like Bgv and BFV does. And also, to give you an idea, there's a sort of trade-off mainly between the second and fourth generation and the third generation, which is typically the second and fourth generation schemes can handle packing very, very well. So it means you can pack a lot of plain text into just one ciphertext. So you can pack as much as 4,000 plain text values into just one ciphertext. But those schemes can only really do addition and multiplication exactly. So meaning that doing nonlinearities, so things like ReLUs, that becomes very hard and very problematic with those schemes. And then as opposed to that, you have schemes like TFHE, which are really, really great at handling some nonlinearities, and they have very fast bootstrapping and so on. But they don't have the same packing capabilities as the second and fourth generation schemes do. So that's a little bit where the generation stands. And again, I will repeat, but I'll say again, I will mainly focus on the second generation schemes. And I thought I'd give you a little bit of a historical flavor of what FHE was and where it's at today. And this is mainly to say that what I'm hoping to convey at this point with the next 2-3 slides is that we've actually seen some phenomenal improvement in FHE and in terms of running times and what we can do with it. And I mean, of course, I'm excited about it because it's my area of research, but hopefully I can convince you to also be excited about this. So I won't go through all of this, but I will tell you that FHE was first proposed as an open problem in 78 in the paper Data Banks and Privacy Homomorphisms, if I remember the title correctly. And then it took just over 30 years to get the first ever scheme, which was Gentry Scheme, which was really just a proof of concept. It couldn't be implemented. It was highly impractical and so on, but it was the first scheme after 30 years of it being an open problem. And it was dubbed the holy grail of cryptography for a long time. I don't think anyone calls it that anymore, but you know, hopefully this conveys that it's not a straightforward thing to achieve. The first implementation then came in 2010, and then, you know, it kind of snowballed a little bit. So we had the second generation schemes in 2012, 2013 was GSW, and I'm making this this claim that I don't think is too controversial at this point, that in 2020, 2021, we're almost at the point where it's commercially viable. If you've looked at, you know, for example, Microsoft, they've been releasing products with Fhe. I think they've released a product that does private set intersection using Fhe, and so on. So I don't think it's too controversial to claim it's almost commercially viable, which again is pretty exciting given that the first scheme was 2009 and it was not implementable. And just to hammer that in a little bit further, so this is from the first implementation, where you can see that, you know, the key generation would take for some parameters, you know, 8 minutes up to, well, 2 seconds up to 2.2 hours. A bootstrapping operation might have taken as long as 30 minutes. And this is some results that we got with my colleagues at Intel back when I was at Intel. And what we achieved, this was 2019 already, so it's scarily perhaps already 2 years ago. You know, we managed to get a throughput of nearly 2,000 images per second for pure Fhe protocol. And then if we were willing to add some a little bit of a hybrid protocol with Fhe and MPC, we were at almost 3,000 images per second. So again, hopefully I've convinced you that this is pretty exciting and it's a big improvement, you know, which not just Fhe researchers should be excited about. And if you're interested further, there's all these actively maintained libraries that are really great, that implement all of these schemes that, you know, you saw in my previous slide with the generations. So I won't go for it anymore, but if you're interested in playing around with it, I do recommend these libraries. They're really great. And I thought I'd also mention the standardization effort, which started around 2017. Of which I am a member of, and what we try to do is do things like writing white papers on applications, API schemes, so on and so forth. We do some work on usability, so, you know, kind of trying to draw out use cases. And then we have an actual standardization proposal that I think was sent to ISO. And this is all, you know, in an effort to make it more accessible, really, especially because if we do get to talk about the maths of it a little bit, and, you know, you'll see that it's quite complicated. And it's, at the moment, still perhaps a little bit is the case that, you know, if you're not an expert in Fhe, then you might not know where to start. So this is all an effort to just make it more accessible. And I won't take you through the applications, for all of these applications, because, you know, there's a reason why it was dubbed the holy grail of cryptography for such a long time. But I've highlighted machine learning there because I think at the moment it's what's looking like the most promising application for Fhe and the most exciting, and especially, you know, in terms of, as I mentioned, the schemes, the second generation and fourth generation schemes that can do a lot of packing. So that's kind of really, really exciting for this. And if you look in the literature, you know, privacy preserving machine learning, there's already quite a lot of literature on doing PPML with Fhe, and it's a growing field of research, and it's, as I mentioned, something that I work on. Okay, so that was a long introduction. but hopefully it was useful information. So let me talk to you, start sort of the first technical part of the talk, which is where I talk about what to me is the most challenging problem in FHE, and that is the noise. So at a high level, so kind of waving my hands a little bit, but to give you some intuition, at a very high level, an FHE ciphertext is essentially a lattice point to which some noise has been added. So we have a 2D lattice here, and then we have this red and blue ciphertext where you pick this lattice point, you add some noise, and then you get this red ciphertext, and then you do the same for the blue ciphertext. So at a high level way of thinking, this is what encryption is. And then decryption, again, is essentially hand-wavingly solving CVP with some secret information. So you take your red ciphertext, you look at which is the closest lattice point, that's it, that's how you decrypt. Okay. But what I want to show you here is that now that you've added these two, the red and the blue ciphertext, and you get the green ciphertext, well, if you wanted to decrypt this, you can already just visually see that you have a problem because it's not immediately clear which is the closest lattice point. So at a high level overview, this is essentially what the noise problem is. So we use noise to encrypt to get security, in fact, to get an LWE instance, which I will define later. But as we do these homomorphic operations, this noise compounds a lot, and it can compound so much, as you can see here, that you may actually lose the underlying message. So here, think of the message as the correct lattice point that this should decrypt to, okay? And now there's two main techniques for managing the noise. One's called bootstrapping and the other one is called modular switching. Bootstrapping is something that is used very efficiently in the third generation schemes. And this essentially corresponds to doing a homomorphic decryption. So you have, and this is a picture from Ilaria Chilotti's talk. So you have this blue ciphertext here. You can see from the thermometer that it has a lot of noise, and it has in fact so much noise that the decryption is might fail. And what you do is that you sort of add this green box, which is essentially adding a layer of encryption on top of this blue box, and within the green box, you decrypt the blue box. And so you haven't completely removed the noise, so you still have security because you have this noise from the green box, but you've removed the blue noise. And then you have something that's called modular switching, which is also sometimes referred to as rescaling. It's a slightly, modular switching and rescaling are different operations. I don't want to go into the specifics right now. But essentially the way they both work is, and these two I should say correspond to the second and fourth generation schemes, where essentially what you do is that, so this is your, visualize this as your ciphertext space. And what you do is that you layer up your ciphertext space in all these layers from L all the way down to 1. And you start at the top, and this is where a fresh encryption will live, so on the very outer ring of your ciphertext space. And then every time you do a multiplication, you go down a ring, and this is essentially an appropriate divide and round operation by which you control the noise magnitude. And this is typically done after each multiplication. The reason for which being, again, if you look at this and use your imagination a little bit, you might be able to see that the noise grows a little bit with addition and a lot with multiplication. So you wouldn't do a modular switching with addition, but you would do one after each multiplication. And so hopefully also with these two pictures, you can see that the second and fourth generation schemes, which mainly use modular switching for noise control, are somewhat homomorphic schemes. And so So you can see that once you get to Q1, you can't modular switch any further. And so you have this predetermined number of multiplications that you can do. And then here with bootstrapping, in theory, you're not really limited. You can keep on doing this. And so typically the third generation schemes are fully homomorphic in that you don't have this predetermined circuit depth that you can evaluate. Okay. And so as I've kind of mentioned, as of now, pretty much all of the efficient or all of the main fully or somewhat homomorphic schemes are based on the some variant of the learning with errors problem, meaning that they all have some inherent noise. And this noise grows during homomorphic operations. And if it's too large, decryption will fail. And another issue with this is that decryption will fail, but you will typically not actually get an indication that it has failed. Which means that a good understanding of the noise growth is essential. First of all, you need it either to determine when to bootstrap or to do a modular switching. And you need to understand this very well because, again, you don't really get like a notification. Is that when I mean decryption will fail, I don't actually mean necessarily the algorithm will fail. It's just decryption will be wrong. So you might get a wrong decryption without knowing about it. And then knowing when to bootstrap or to modular switch, in particular when to modular switch, is essential for us to choose appropriate parameters. And ideally, we want them to be as small as possible because large parameters kind of remain one of the major challenge in practical HE. So again, if you kind of look here on the modular switching, you can see that, you know, you this will guide your parameter selection. So if, you know, first of all, the more multiplications you have, then the more layers you're going to have. And then if your Q1 needs to be a certain size, then that's going to influence all of the other Qs, meaning that your first ciphertext modulus is going to be huge. Okay, so hopefully I've convinced you that it's quite an important problem. I wanted to illustrate this a little bit with something perhaps a little bit more optimistic in terms of the impact that some modifications can have on on this noise growth, and how much impact kind of just tweaking your algorithms a little bit can have in terms of practical results. So this is also something that we did in the paper that I mentioned previously, the ngraph HE2, with my previous colleagues from Intel, some of them still my colleagues actually. And we did what is so-called lazy rescaling. So rescaling is the analog of modular switching in CKKS, which is that we only did a rescaling after either a fully connected or a convolution layer, and we also just skipped it if there were no multiplications left before decryption. So we kind of scanned the circuit ahead. And as I mentioned, you would typically do rescaling after each multiplication, but if there were no more multiplications left before decryption, we just skipped it. And so here were the results of doing this. So if you look, you know, with just the first two lines, which I guess are the most easily comparable, you know, we got about an 8x improvement from doing this, which is a simple tweak, and it, you know, it really allowed us to boost the performance. So again, hopefully this kind of illustrates how important it is to really understand the noise behavior in your scheme, and B, how much impact it can have if via this good understanding you tweak the way you implement some algorithms or when you decide to use them in order to gain efficiency. And then the last thing I'll say about this, because you might be wondering at this point how hard it is to do this, and the answer is fairly, at least for some schemes. So this is a paper that I wrote with my co-authors Kim Line and Rachel Player. where our aim was essentially to evaluate the effectiveness of theoretical noise analysis. And what we found is, so you can look at the columns where E is the estimate and X bar is the measured noise growth. And you can see that in some cases, the difference can be as much as 20 bits between what we predicted the noise growth would be and what the noise growth actually was. Which is an issue again, because this would lead us to choosing very high parameters when we perhaps don't need them to be as high. And so the only additional thing that I will say here on this slide is that this again, so this was for the schemes BFV and Bgv. So this is for the second generation schemes. It's in fact particularly hard to measure or predict the noise growth in these schemes. And the reason for this is that the multiplication operation is nonlinear. And so our initial noise is sampled as a Gaussian, but because the multiplication operation is not linear, we cannot model it, continue to model it as sub-Gaussian. So we have to do a worst case analysis, which means that our bounds blow up. And I will also say that in schemes like TFHE, this is actually not a problem, which is really great for them, because they their bootstrapping operation is they manage to do it in a linear way so that all of their parameters remain sub-Gaussian, which means that they can actually do an average case analysis. So this this issue of having this huge gap that we call heuristic to practical gap in the paper is rather specific to the second and fourth generation schemes. It doesn't apply to the third generation schemes. Okay, so I'm about half an hour in. I will talk a little bit now about the mathematics of FHE. Again, I don't really want to go into huge amounts of detail, but hopefully I can just give you a little bit of flavor of what's happening. So this is the learning with errors distribution that I mentioned previously. Which is as follows. So in the learning with errors problem, you have a secret vector, and then you have distribution chi, which is typically in our applications we choose it to be a Gaussian, a discrete Gaussian. In fact, it doesn't have to be that, but this is what's typically chosen in FHE land. And so given these things, and you also have a modulus Q, which I didn't write, but I should have. So given all of these parameters, an LW distribution is a pair of elements where the first element is a vector AI that's generated uniformly at random. And then the second element is an element of ZQ that's created via the inner product between AI and the secret key, to which you add some noise, some Gaussian noise. Again, doesn't need to, but this is what we use in LWE. And so given this, the decision LWE problem is to distinguish whether in presence of pairs that look like this, that look like AI, BI, it's to decide whether these pairs were sampled uniformly at random from ZQN cross ZQ or from the LW distribution. And then the search problem is to recover the secret. Okay.
Anna?
Yeah.
We have some questions from Christian Pascu. I don't know if Christian, you can unmute yourself.
No, I think they can't, Edu. So maybe you can read.
Okay, so Christian is asking whether the noise sampling impacts the security. And then the second question that maybe there's more to say as well is if this noise sampling impose restrictions on the other chosen parameters like the ciphertext modulus, plaintext modulus, etc.
Okay, so in some sense, the noise sampling is what creates the security. So again, because we're gonna the encryption or a ciphertext rather is going to be an instance of this in fact ring LWE problem, which is on the next slide. So then the answer to your question would be yes, but it doesn't so much impact the security as much as it creates the security. And then yes, it does also impact your modulus and also your n here. So to get security, it's gonna be an interplay between the width of your Gaussian if you are using a Gaussian, but even if you're using uniform random, you can model it as a Gaussian. So it's gonna be an interplay between the width of your Gaussian, your q, and your n. Does that answer your question?
I imagine so. If he doesn't complain, you can. Yeah, he says yes.
Oh. You can just ask some more if it doesn't. Okay, cool. Thank you. So I'll then move on to defining ring learning with errors, which is essentially a structured, more efficient variant of LWE. And you can see that it's very similar, except that now instead of, so you can see here we were sampling A in this space here. Now we're looking at polynomials. So you have your polynomial f here, which is monic irreducible in Zx of degree n, and then you form this ring R. And then you form this ring RQ, which is essentially polynomials with integer coefficients modulo your polynomial f modulo your modulus q. I should also say what I'm defining here is actually poly LWE and not ring LWE. The reason for that is for a talk where I'm not going into a lot of technical details about the LWE problem. It's actually just easier to state and to read. But it's worth mentioning. And so then you, very similar to LWE, you sample your AIs uniformly at random. You have your chi, which is a discrete Gaussian distribution. Usually we take it to be centered around 0. And also has to, I mean, I'm sweeping a lot of things under the carpet, but that aren't necessarily relevant for this talk. But of course, you have a lot of conditions in terms of, you know, how chi looks, what it looks when you embed it in the canonical space and so on. But I don't think it matters too much for this talk. And so then you have your AIs again that are uniform at random. You have your Gaussian errors EI that are sampled from this discrete Gaussian, and then you form this inner product, which is now, sorry, it's not an inner product anymore. It's a polynomial product. And so the decision problem again, like in LWE, is to distinguish, you know, given pairs that look like this, is to distinguish whether they come from the ring LWE distribution or if they come, or if they're sampled uniformly at random. And then the search problem is to recover the secret S. Okay, and so this is the hard problem that, again, most FHE schemes are based on, at least the ones that are the most efficient, and certainly the ones that are considered for standardization currently in the HE standards group. And so now I thought I would give you a little bit of a taste for what an FHE ciphertext looks like, because I've described all these things. I talked about noise, talked about the problem, but I thought I'd show you what an FHE ciphertext actually looks like. And so a scheme, again, here I'm talking about second generation scheme. So it's parameterized by a dimension n, which we typically choose to be a power of 2, meaning that the polynomial that we pick is a power of 2 cyclotomic. So phi of n here is your f here in the definition. And then we have this polynomial ring RQ. Again, you have a modulus q. There should be a q here. That's a typo. But you have your polynomial ring RQ, which is the set of integer polynomials mod q mod phi of n. And typically in Bgv or BFV, you would have 2 numbers, p and q. P would be your plaintext modulus, and q would be your ciphertext modulus. And then in the parameters, we also have a ciphertext modulus capital Q, which is created by picking L primes, P0 to PL minus 1. And then we have this chain of moduli that's formed as QK is equal to the product of these primes from 0 all the way up to K. And then your capital Q is the product of all of the primes. And so if I go back a little bit, just so you understand where that comes from, this is what this is. Okay, so if you remember, like this is Q1, Q2, and so on and so forth. And this would be P1. The next one would be P1 times P2, and then all the way to the top. So that's where that comes from. Okay, and then we have an error distribution of standard deviation sigma. Again, typically, the case where I'm talking about, this is a discrete Gaussian centered around 0. Sigma is 3.2 always in applications. We have a secret distribution, which is typically uniform binary or uniform ternary. In FHE, we used to use low Hamming weight secret key until that was kind of shown to, unsurprisingly, facilitate some attacks. And so this would usually, so if you look at the standards, the set of parameters that are considered in the standards are uniform binary or ternary. You have a plaintext modulus T, and then you have a security parameter lambda, as usual. And then, so here is the Bgv scheme that I'm showing, and I'm not going to go into too much details, but it's just to kind of give you some idea of what this looks like. So you have this secret key SK, which comes from this typically uniform binary or ternary, which is just this here. And then from that, you create your public key, which is hopefully you can see an LW instance, or a ring LW, or in fact poly LW, I should say. So the public key is it says R there, but really what it should say is poly LW sample. And then encryption is essentially done by, so this is your message M, and then you have the first part of your public key, and then you have another Gaussian error. And then the second element of your ciphertext is the second part of your public key, and then another Gaussian error. And these are all multiplied by T because here, if you look at decryption, we're going to take, so decryption is this C0 minus the secret key times C1. If you kind of stare at this for long enough, you will see that it indeed cancels to BM if the noise is not too large. And then we take this modulo T. So this is where these T's come in so that the Gaussian errors go away upon decryption. Addition is quite easy in these schemes. It's just, you just add coefficient-wise your ciphertext. And then multiplication, as I kind of mentioned earlier, is a lot more involved and a lot more complicated. It essentially involves performing a tensor operation. So if you have, C0, C1 and C0 prime, C1 prime, you form this intermediate 3 elements tensor ciphertext, which is C0 times C1, C0 prime plus C1, and so on. And then you do what is called a relinearization, where you map this intermediate ciphertext to a 2-element ciphertext so that it looks, like this, like a normal ciphertext. And hopefully this should also give you some intuition as to why the noise growth in these schemes kind of really blows up when we do multiplication, and also why it's a nonlinear operation and why it's hard to do like an average case noise analysis on it. Okay, now I'm getting close to I think I'll talk for maybe 5 more minutes, and then we can have time for questions if there are any more. So I will go for this a little bit quickly. But I wanted to talk about this double CRT representation because I think this is one of the very, very cool features of FHE and one of the very, very cool ways that maths is used in this, and it's used for us to get a huge efficiency improvement. And so you might remember that I said that we work with the cyclotomic, the power of 2 cyclotomic polynomial, x to the n plus 1, where n is a power of 2. And this represents the mth cyclotomic polynomial. And so we will pick our q's, and in fact, this translates to picking every single, let me go back, every single one of these to have a primitive root of unity, a primitive mth root of unity. And so if we pick this appropriately, then phi of n is going to factorize into linear factors mod q. And then also remember q, you know, as I showed you on the previous slide, it's a product of L prime factors. And so what this means is that, so let me show you the ring again. So here, there's a q missing, but remember that our polynomial ring is the ring of all integer polynomials modulo q, which is this, modulo phi of n, which is this. And so what that means is that we can actually apply the Chinese remainder theorem twice. So once with respect to the polynomial and then once with respect to the modulus q, which means that we can represent a polynomial in our ring RQ via what is called the double CRT representation, which is evaluated simply by taking your polynomial, evaluating it at all of the relevant zeta i's, mod each of the PJs. And the advantage of this is that once you have this representation, then your homomorphic operations become a lot easier to evaluate because it's now coefficient-wise. So you're, instead of multiplying polynomials, you're actually just doing like a Hadamard multiplication, which is really great. And so this can be computed essentially by invoking the FFT algorithms L time mod each of the PJ. And so this is really great. It's a really great way of, you know, gaining efficiency, and I think it's a really neat trick of, you know, using maps in cryptography. So I did want to mention it. And then also for those of you who know a little bit more maths, you can also use the action of the Galois group by just permuting the columns of your matrix appropriately. If that didn't mean anything to you, then just ignore it. Okay, so I've reached the conclusion now, so I'll talk for a few more minutes. So to conclude, in the 2nd generation and 4th generation schemes, which is what I really focused on this talk, we saw that we can homomorphically do additions and multiplications, even though multiplications are expensive, but we can do them. And now, is this an issue, just being able to do only these 2 operations? And the answer, unfortunately, is yes, because for some applications, especially if you remember my slide about applications, I highlighted machine learning as being kind of one of the very promising use cases or applications for FHE. And typically in machine learning, your activation function is not going to be a polynomial. So it's typically going to be something like a ReLU or a maxpool or so on and so forth, which means it's nonlinear, which means for these schemes, it's a bit of an issue. So we would typically approximate with a Taylor series, for example. Or even there's cryptonets, for example, they approximate the ReLU with the activation function x squared. But of course, this means that we have a larger multiplicative depth. So if I just take you back for a second here, So this means that this becomes a lot bigger. There's a lot more layers. Your ciphertext becomes a lot bigger. Your key becomes a lot bigger. So if you remember that we encrypt here, this is like your top ciphertext. And so having more multiplications or having a higher multiplicative depth is a bit of an issue, because it means that it blows up your parameters. If your parameters are big, then it's, your implementation is going to be slower, and so on and so forth. And so typically that means that when we try to, say, do machine learning or evaluate anything that's nonlinear homomorphically with these second and fourth generation scheme, we get a bit of a trade-off between efficiency and accuracy, because of course the Taylor series, the higher you go, the better it approximates your function. So there's a bit of a trade-off there. I will say something else, which is with the third generation scheme. So for example, TFHE, they can do some nonlinear functions exactly. So for example, ReLU, they can evaluate a ReLU exactly homomorphically, but they don't have the packing capability. So it's if you're thinking about, okay, which is the best FHE scheme, or which one should I use? Well, it kind of depends. If you are not computing on a lot of data and you have an activation function, or a function that you want to compute, whatever it is, that has nonlinearity, then maybe something like TFHE would be better. But if you have like a really big database that you want to compute on, or just a lot of data, then you might be better off trading off some accuracy for the capability of computing on larger amounts of data at a time, of parallelizing essentially. Okay, and I thought the last thing I will say is that I would mention some of the remaining challenges in FHE, and I have focused exclusively on second generation schemes here. So one of it is noise analysis. So it would be really great if we could, get rid of that heuristic to practical gap that I mentioned earlier. It would be really, really great if we could get a tight noise analysis, so that we could set our parameters as efficiently as possible, and not sort of essentially waste any space, not predict that we're going to have a noise growth that isn't going to be there, and that's just, wasted space. Efficient bootstrapping would be great for second generation schemes. I didn't really mention it, or I did in passing, but there's kind of a trade-off between, efficient bootstrapping, but no or lesser packing capabilities in third generation schemes, and then really great packing capabilities in second and fourth generation schemes, but no efficient bootstrapping. So if we could get efficient bootstrapping or more efficient bootstrapping in these second and fourth generation schemes, that would be great. And this kind of goes hand in hand with being able to evaluate nonlinear functions in the second generation schemes, because that would also be, it would be a huge improvement, and it would be a huge advancement for usability, especially in things like privacy preserving machine learning. And before I close and say thank you, I will obviously say this is a non-exhaustive list, and I'm sure we could spend hours about what are the remaining challenges in FHE. But with that being said, thank you very much for your time, and I will take any questions now.
Thanks a lot, Anna. Great talk. So let's see. We have, let's start with this question. So Emanuele Bellini is asking, are there other mathematical structures besides lattices that are used for FHE?
Yes, there are, but they are, so there are a few papers that are, I think, using non-abelian cryptography to build FHE, but as far as I know, they don't have a security proof. And so it's kind of, this is what I meant by the main ones, meaning, they've been scrutinized, they have security proof, and we're considering them for standardization, and they are efficient. Those are all lattice-based.
Okay. And then we have another question by Pratiska Raju. Sorry, I'm surely pronouncing this wrong. So they have read about quantum FHE, and I think there's like two questions from the same person. They are both interested on like the quantum resistance of Fhe and about quantum Fhe, which are like two different things. So I don't know if you could say something about this.
Okay, so because it's lattice-based cryptography, we kind of expect it to be quantum safe. I don't know if there's a more specific question to that, but we're not. This very much fits within post-quantum crypto. And then as far as quantum Fhe, I don't really know because I don't really understand quantum crypto and I don't work on it at all. But I seem to remember that there has been some work on this in the literature, but I don't know how much I'd be able to comment on it in terms of, is it efficient? Does it have a security proof? Is it, yeah, I haven't read the papers because I don't really work on quantum crypto, but I seem to remember, take this with a grain of salt because I might be wrong, but I think there are some people that are working on that.
Okay, so they're happy about the answer.
Yeah.
And we have one last question where I think I'm going to stop pronouncing names to not do it wrong. What are other machine learning algorithms that are Fhe friendly?
I mean, that's a great question. We're kind of at the beginning. So there isn't, that's a great question that I would like to know the answer to. There isn't like a unified framework or a unified anything really when it comes to that. So far it's just kind of been like, pick this thing, can you do it? So, there's CryptoNets. There's what we did with ngraph HE2. There's the iDash competition that is actually really great, and to be honest, is the closest thing that comes to benchmarks as far as Fhe and machine learning, or just Fhe and these kind of privacy-preserving genomic computations go. Which is a competition that happens every year, and there's a task to do, and there's 4 tracks. So there's TEs, and then Fhe is always one of the tracks. And so one of the years it was genomic imputation, and they actually managed to do that pretty fast. So the 2019 winners were TFHE, the TFHE team, and then I think the runner-uppers were CKKS. So that should give you some indication that they managed to do it with both schemes. But yeah, no, there isn't a general answer to this, unfortunately, but hopefully it's something that we'll work on.
Sounds fantastic. Okay, there's another question. I think maybe we're bombarding you a little bit about whether you find any drawbacks about combining multiple homomorphic encryption schemes like they do in Chimera. I don't know, or whether there are some situations. Yeah, are there any drawbacks to this?
I don't know, and because. Well, one of the reasons is that the Chimera implementation isn't really available anymore. So I think something like that is extremely promising, because ideally you could or you might get to the point where you can, do the nonlinearities in TFHE and then kind of map back somehow to CKKS and be able to have the packing capabilities. So that's a really promising thing. I think. If I'm not wrong, the 2018 winners of the iDash competition, or one of the top 3 people, actually did use Chimera. So, and there was an implementation that was available at some point. So as far as I can tell, but without an implementation, without more concrete results, it's kind of hard to tell if there are any drawbacks. But that is a very promising, avenue of research.
Okay, so I think I have. Let's have a final question just to close up. So Mukul is interested on what's your take on differential privacy versus like FHE regarding like privacy preserving machine learning. Of course, like these are solutions to different problems, but maybe you want to say something about this.
Can you say that again? I don't think I really understood the.
Okay, so the specific question is if you could elaborate on the using FHE versus using other approaches like differential privacy for privacy preserving machine learning.
Well, I definitely don't think there's a one size fits all now, and I don't think there's going to be a one size fits all ever. And so my take would be, you know, see kind of what works. I mean, even with machine learning, you know, there isn't like just a box that you can use. You know, that's like, okay, you get your model. Typically, you know, it's a lot of trial and error, and you try different things and you just see whatever gives you the most accuracy. So I think it really, you know, privacy can mean so many things for so many different people, that I think they're all great solutions that answer different problems. You know, you could see in the snippet that I showed of our ngraph HE2 paper, we had one solution where we used pure HE, and then we had one solution where we used it's not, we called MPC, but it's not MPC in the sense that you might think of, but like a interaction between the client and the server. And so if you're in a setting where that's not an issue, then that actually gives you a huge improvement in timing. So yeah, my answer is, I think, depending on your use case, depending on what you're trying to do, depending on who you are and what your definition of privacy works, the best solution for you is probably going to look different from the best solution for me.
Okay, I think that's a great answer, and there are no other questions. So thank you very much, Anna, for this talk. And yeah, hopefully we can do it in person at some point.
Thank you. Thanks very much for having me.
Yeah, thank you.